All right, problem one, we have a chi-square test is used to test whether a 0 to 9 spinner is fair. That is, the outcomes are equally likely. The spinner is spun 100 times and the results are recorded. The degrees of freedom for this test will be, okay, so the degrees of freedom in this case would be equal to the number of categories minus 1. So the number of categories minus 1. And the number of categories are the numbers 0, 1, 2, 3, 4, 5, all the way to 9. So there's actually 10 categories, 1 through 9 and 0. So the degrees of freedom will be equal to 10 minus 1 or 9. And so the answer will be B. All right. Problems 11.2 and 11.3 refer to this setting. Recent revenue shortfalls in a Midwestern state led to a reduction in the state budget for higher education. To offset the reduction, the largest state university proposed a 25% tuition increase. It was determined that such an increase was needed simply to compensate for the lost support from the state. Separate random samples of 50 freshmen, 50 sophomores, 50 juniors, and 50 seniors from the university were asked whether they were strongly opposed to the increase, given that it was the minimum increase necessary to maintain the university's budget at current levels. Here are the results. Okay, so it looks like they broke it down, again, according to grade, freshmen, sophomore, juniors, seniors, the ones that said they were okay with it, or the ones that did disregard if they were strongly opposed. 39 freshmen were strongly opposed and 11 of them weren't. So for each grade level. So which hypothesis would be appropriate for performing a chi-square test? Okay, so this is a chi-square test of homogeneity, because you have basically categories across, and then you have different answers that get for each category. So you have a matrix of rows and columns. The previous example was simply just one row. This is remember, this is 2 rows by 4 columns. So chi-square test for homogeneity, and the null hypothesis, your HO, is essentially, remember, there's no difference in the distribution of answers, or that all the distribution of answers are the same for each group. Meaning that, let's say if it was that each group would answer the same proportion. It doesn't mean that they all have to be 50% yes and 50% no. It just means that if they would all be 40% yes and 10% no, if that was the proportion. So there's no difference in how each group answered yeses versus no. So the alternative is that there is a difference. There is a difference in the distribution of yes answers and no answers for each grade. In other words, that we're saying that the percent of freshmen that said yes versus the percent of sophomores that said yes would be different. And likewise, the percent of juniors that said yes would be different from the percent of sophomores that said yes, and so forth. Now, you wouldn't need at least 2 of them for it to make sense. So, because otherwise, because you need at least a difference between 2. In other words, the other 3 could be the same, but 2 of them would have to be different. So let's look at which one would make sense. So the null hypothesis. Closer students could agree. Nope, no, we don't care, but we're not really getting into that. The null hypothesis, the mean number. No, we're not looking at mean number. The null hypothesis is that the distribution of student opinions for the proposed tuition increase is the same. Yes, is the same for each of the 4 years at the university. The alternative is that the distribution is different. Those are the keywords. The distribution is different and the distribution is the same. So your answer is going to be C. Now, problem 3, the conditions for carrying out the chi-square test in exercise 11.2 are independent random samples from the populations of interest. All expected counts are at least 5. And the population sizes are at least 10 times the sample sizes. Okay, independent random samples are a population of interest. Let's first check if that one's met. So we want to see which ones of these are met. So let's first check to see. So we're told separate random samples are used. So that first condition is met. All expected counts are at least 5. So expected counts, in other words, if the null hypothesis were true, what would you expect for each proportion to or each yes and no to be in each grade level? And one simple way to check this is like, yeah, you can enter these in the matrix or do the equation, row total times column total divided by overall total and calculate that. But when you see that they're all at least 5 just by looking at them, then the expected counts would be at least 5. These are observed counts, but still, it just logically makes sense if they're all at least 5. Then the expected counts would be met. And the problem is that if let's say if any of these were like 1 or 2 or 3, if any of these values are below 5, then you have to go through the math to at least check that one. But since they're all shown to be at least 5, that's going to be met. And population sizes are at least 10 times the sample sizes. So can we say that there's at least 500 freshmen, 500 sophomores, 500 juniors, and 500 seniors from the university? And yeah, definitely, since this is a large university, and pretty much almost every university has at least 2,000 total kids. So then that's met. So actually, all 3 conditions are met. So our answer is going to be E.